So if we continue on, it says, in mathematics, there are certain methods and rules of argument that mathematicians use to convince someone that a conjecture is true, even for the cases that extend beyond the observed data set. So that's what I keep saying. We got to prove that these conjectures go beyond our little silly examples that we show. It goes off for, to infinity and beyond, right? Buzz Lightyear. Just a little side note, this argument, this is not like a disagreement. This isn't a fight. That's not what we're talking about. This is a series of reasons and facts to support a given statement. So we, as mathematicians, we have to come up with a legit argument to convince someone that a conjecture is true. We can't just say, because I think it is, or because I said so, right? That doesn't work anymore, because I'm sure your parents say that when they ask you to do some chores or ask you to do something, when you're like, why? And they said, because I told you so. That's not a legit argument. I wouldn't suggest that you tell your parents that, but, that we're not allowed to do that in geometry class. We got to come up with a legit series of reasons and facts using properties and postulates to support a given statement, to prove a conjecture. So it says these rules are called rules of logical reasoning and rules of deductive reasoning. That's the term we're going to use, deductive reasoning. An argument that follows such rules is called a proof. Now, I've already introduced y'all to proofs. That example back in activity 1-2, where I convince you, I show you, I prove to you that the measures of vertical angles are equal. So if you have vertical angles that are congruent, they have the same measure. I walked you step by step through a proof, and I gave you statements, and I gave you reasons why I'm saying those statements. So I used deductive reasoning. I came up with a legit argument. It was that proof. An argument that follows such rules is called a proof. We already talked about that. A statement or conjecture that has been proven, that is established as true without a doubt, is called a theorem. So you have a conjecture that you've created using your inductive reasoning, right? So you collect data, you analyze that data, you find patterns, you make a generalization called a conjecture. You test that conjecture. If it seems right, then sweet. If it's wrong, you go back to the drawing board, you collect more data, you come up with a new pattern. Once you have a good conjecture and you are almost positive that it's true for all cases beyond the observed data, that's when you come up and formulate an argument that follows the rules of deductive reasoning called a proof. That proof transitions or transforms that conjecture into a theorem. That's exactly what this says. A proof transforms a conjecture into a theorem. In my class, you're going to have to give me a step-by-step explanation of how you go from a pattern or a collection of data, finding a pattern, and then getting it down to a theorem. So make sure you re-listen to what I just said and you're able to describe that to me. It says below are some definitions from arithmetic. So we have even and odd integer. An even integer is an integer that has a remainder of 0 when it's divided by 2. We're talking about old school division here, right? So we're saying 2 divided by 168. And so we're saying, oh, that goes into 16 twice. And so you'd say that and subtract it, 0, bring down the 8, and 2 goes into 8 4 times, and so on and so forth. And we get this remainder of 0. That's what we're talking about here. And then an odd integer is an integer that has a remainder of 1 when it's divided by 2. So if I just change this up a little bit and say, well, what if we took 2 divided by 169? Well, we bring it down to 9. 2 would still go into 9 4 times, but then voila, we have that r, that remainder of 1. So if that happens, that means that integer is odd. What we're going to do is we're going to collect some data in items 1, 2, and 3, and from that data we're going to make 3 separate conjectures. They all involve even and odd integers and finding the sum of these even and odd integers. So it says, in the following items, you will make some conjectures about the sum, so addition, right? Addition of even and odd integers. Item 1, it wants us to look at the sum of some pairs of even integers. So I'm going to say even plus even equals what? On the second one, they want us to look at what you get when you sum up two odd integers. And then on the last one, we're going to mix it up a little bit. And we're going to have an even and an odd. So what type of integer is going to come out? Well, let's collect some data. If I have an even integer like 2 and another one 4, that's going to be 6. So it seems, I got an even integer. What if I go bigger? What if I say 14 and 16? Well, that's going to be 30. So that's still another even integer. And then what if I have, let's go some negatives. So negative 8 and plus a negative, I don't know, 10. That's going to be a negative 18. So it seems as though when I have an even and plus an even, I'm going to get another even integer. My sum will be even. If I have some odds, so 7 plus 11, that's going to be 18. And then let's say 9 plus, I don't know, a negative 3. That's going to leave me with 6. Let's say I have a negative 5 and I add 17. Well, that's going to give me 12. So it seems like when I have the sum of two odd integers, whether it's positive or negative, I'm going to get an even number as well. Number 3, we're doing mixing it up a little bit, even and odd. So an even integer plus an odd. So let's say, I don't know, 2 plus 7, that equals 9. And let's go with 4 plus 21, that's 25. And let's take a big number, 74 plus 101, that's 175. So it seems as though when I mix it up and have an even and an odd, odds are spit out. So I haven't proven these conjectures yet. These are simply conjectures that when you take the sum of two even numbers, the sum will be even. If you take the sum of two odds, that sum will be even as well. And then when you mix it up, even and odd, you're going to get an odd. So we have these 3 conjectures. We're going to prove these conjectures are true for all cases, making it into theorems 2 ways, geometrically and algebraically. So let's do the geometric way first. So go over to the next page. Up at the top it says the following items will help you write a convincing argument, aka a proof, that supports each of the conjectures you made in items 1 through 3. So we're going to write a convincing argument, a proof, that those 3 conjectures are true. So here we go. So figures A, B, C, and D are puzzle pieces. The world's easiest puzzle, apparently. Each figure represents an integer determined by counting the square pieces in the figure. So let's talk about that. Figure A is representing some integer, and if I want to figure out what integer it's representing, I'm just going to count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So figure A is representing the integer positive 10. 10 is also the area of this rectangle, right? So if I want the area, that's 2 times 5, so that's 10. So there seems to be this relationship between the area of these shapes and the integer that it's representing. That's going to come in handy a little bit later down in the road. And then it even works for these as well, because I can say, well, let's find the area of this rectangle here by saying 2 times 5. And then I just know I got to add that 1 there. So it's going to be 2 times 5. And I'm going to add 1 to it. So this figure C is representing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is 2 times 5, that's 10, plus 1. So again, it seems the area of these shapes is the integer in which they are representing. So I understand, and I clearly see that this is representing 10 because it has 2 rows and 5 columns. This is representing 6 because it has 2 rows and 3 columns, so on and so forth. But instead of recognizing these are 5, I'm just going to put this as a variable because these are integers and they can be any integers they want. And as you can see, these puzzle pieces all have 2 rows. So this 2 is pretty much going to stay consistent. What's changing is how many columns you have and whether or not you have full columns. So I'm going to call this is a 2 by P, and this one's going to be a 2 by M. And then if we look, this figure C is made up of this rectangle. So I'm going to say that this is a 2 by P, and then I got to add that 1, and this is going to be a 2 by this rectangle here. It's going to be a 2 by T, and then I'm going to have to add that 1. So just notice that there is a correlation between the area of these figures and then the integer in which they are representing. It says use these figures to answer the following questions. So let's take a look at what they're going to ask us. It says which of the figures can be used to model an even integer? And that would be figures A and B. Because their area, they're rectangles. They're these rectangles, and their area are even integers. Which of the figures can be used to model an odd integer? That would be figures C and D. Okay, figs, it's just figures, okay? Not fig Newtons. So if you're hungry, you're probably thinking food. But this is figures A and B, figures C and D, correlating with these guys up top. And we know that these are odd numbers because, for instance, let's take this guy right here and bring it on down. If I want the area, I'm going to have to say, well, 2 times T, that'll give me the area of this rectangle, and then I have to add 1 to it, and that will give me that area of that last one. And so that will give us an odd integer. It says compare and contrast the models of even and odd integers. Well, there are differences, but let's look at the similarities first. I want you to notice that all have 2 rows of these tiles or whatever they call them, these square pieces. So let's write that, square pieces. That's what's consistent throughout all of them. They have 2 rows. All of them contain 2 by something rectangles. So if you look at figure A and figure B, these are 2 by 5 rectangles. That is the entire shape. So yeah, the entire shape contains that 2 by something rectangle. Here in figure B, that's a 2 by 3 rectangle. So, but back to these odd integers, they contain these rectangles here. So this one, figure C, it has a 2 by 5 rectangle, but then we have this plus 1. Here on figure D, it's a 2 by 6 rectangle, and you have to add the 1. That's what I mean by they all contain this, quote, 2 by something, 2 by some number rectangle. And remember, those rectangles, they have to have the 2 rows, and then the columns have to be full columns in order for it to be a rectangle. Can't have like a fourth of a column.